Hello. In this video, I will discuss an important tip for when dealing with complex simulations. Let me first quickly show you some examples where the simulation is relatively easy as a comparison. Let's say we want to simulate a droplet on a smooth, curved solid surface. Then, the simulation is typically very easy. We select the solid surface as constraint for the droplet's boundary. Then, we set the desired degree of mesh refinement in the equilibration settings. And, if we want to change the volume defined by the droplet's initial mesh, we set the droplet's volume variation using this option. We can now launch the equilibration, and this will return us the equilibrium shape of the droplet for the input parameters. This simulation was easy enough to set up, and is relatively fast to be run. Even though we set a very high degree of refinement for the fluid interface mesh. The simulation was quick because the droplet's equilibrium shape has a three-phase contact line with a simple and smooth shape, and the droplet's mesh initial shape was close to the equilibrium shape. Let's see another example where the simulation is quick. Say we want to calculate the capillary deformations of a flat meniscus near a solid cube, tilted in this orientation. We have introduced a flat circular fluid interface mesh to represent the meniscus, and created a hole in its center to place the cube. Now we select the constraints for the mesh boundaries. For the external boundary, we select to displace its vertexes only vertically. And we set a contact angle of 90 degrees. In this way, we will mimic a flat interface far away from the particle. For the boundary of the mesh's internal hole, instead we select the cube as constraint. As Young's contact angle on the cube, we also use 90 degrees. In the equilibration settings, we set the desired refinement of the mesh. And because we are simulating a particle at a flat meniscus, we enable the option to allow volume exchange between the fluids. In this way, the flat meniscus will adjust its height with respect to the particle to the equilibrium height. After launching the equilibration, the equilibrium shape of the meniscus near the particle is computed very quickly. The simulation was quick because, firstly, the three-phase contact line of the meniscus along the cube has a simple and smooth shape, despite the sharp corners of the cube. Secondly, the meniscus initial shape was already close to the equilibrium shape. Now instead, I will show an example where the fluid interface's equilibrium shape has a more complex shape. This is the equilibrium shape of the fluid interface that we want to simulate. It represents the interface between two fluids in a cylindrical container with a rectangular blade located inside it. Gravity was not enabled during the simulation, so this could represent a propellant tank in microgravity, or a sub-centimeter cavity on Earth. Young's contact angle is 30 degrees, both on the cylindrical tank inner walls and on the blade walls. So, the fluid below has a strong wettability on these surfaces. Because of the high wettability, at the equilibrium the fluid fills up the whole interstice between the blade and the cylindrical container. Compared to the previous examples, this fluid interface's equilibrium shape has a very long three-phase contact line. And it is located within a solid concave surface. Therefore, the simulation requires some extra care. So, I will now show you different approaches to simulate this fluid interface's equilibrium shape. Let's start from a configuration where there are only the two solid surface meshes. Let's add an initial fluid interface mesh, which we will then edit opportunely, to obtain the correct topology. For convenience, I choose the circular meniscus, and I set its radius equal to the cylindrical container radius. Now that the fluid interface mesh is loaded, we need to edit its topology opportunely to correctly represent the fluid interface mesh that we want to simulate. Therefore, we need to create a hole where the blade is located. For doing this, we launch the Remove Facets tool for the fluid interface mesh. And we use it to select and remove the mesh facets near the blade. This is not yet the correct topology for the fluid interface mesh, because we need to close the hole around the blade. By connecting these mesh boundaries. For convenience, we are first going to refine the mesh facet on the upper boundary. For doing so, we use the Refine Facets tool. Now that we have created this new mesh vertex, we are going to use it to create a connection to the opposite mesh vertex. For doing so, we'll launch the Add Facets tool on the fluid interface mesh, selecting the option by connecting boundaries. Then, we select the first mesh boundary vertex to be used to form the connection, and we confirm it. And then, we select the second mesh boundary vertex to be used to form the connection. These yellow facets show a preview of the connection that will be formed. We click Add Facets to confirm this edit to the mesh. Now the mesh has the desired topology, that is, with a hole around the blade. Let's change the names of the two boundaries of the fluid interface mesh to remember which one is which. This is the external boundary, that is the boundary wetting the cylindrical container's walls. So the other boundary of the fluid interface mesh is the boundary of the hole, that is the boundary wetting the blade. We can now select the constraints for the two boundaries of the fluid interface mesh. For the external boundary, we select as constraint the solid surface mesh representing the cylindrical container. For the internal boundary, instead, we select the solid surface mesh representing the blade. This constraint cannot actually be set, because we got the error, boundary facets on both sides of the solid surface. As we discussed in a previous tutorial video, this error occurs when the fluid interface mesh has some edges, going from a boundary vertex to an internal vertex, originating from opposite sides of the solid surface mesh selected as constraint. In this case, we can see immediately that the problem must be caused by these two mesh edges, going from a boundary vertex on the blade to the mesh internal vertex to the right of the blade. We should be able to solve it by simply removing these facets of the fluid interface mesh near the blade, and then reselecting the blade as constraint for the fluid interface mesh boundary. So we are now using the Remove Facets tool to select and remove facets from the fluid interface mesh. Because both boundaries of the mesh were edited, we now need to reselect the constraint for both boundaries. Again, we set the cylindrical container as constraint for the external boundary. And for the internal boundary, we select again the internal blade as constraint. And this time the constraint is successfully selected, because all mesh internal edges, connected to a boundary vertex on the blade, now propagate from the same side of the blade surface. Some facets of the fluid interface mesh are now overlapping here, but this mesh defect will be automatically fixed during the equilibration, so we don't need to worry about it. For convenience, I save this configuration, so we can reload it later. Let's then try to run a simulation like we did before. In the equilibration settings, we have selected a high degree of refinement for the mesh. In addition, because the fluid interface mesh is confined inside a concave solid surface, we ensure that this option is enabled, which is important to avoid problems due to the solid surface's concavity, as I discussed in a previous tutorial. And this option has been included in Interface Equilibrator since the version 1.0.2. We leave all the other equilibration settings to their default value. And we are now ready to launch the equilibration. This time, differently from the previous examples, the initial shape of the fluid interface mesh is far from its equilibrium shape. In particular, the fluid below the interface wants to fill the whole interstice between the blade and the external cylindrical surface. So the fluid interface mesh will keep rising until the top of the blade. The automated method to refine the mesh is supposed to trigger the mesh refinement when it detects that an equilibrium has been reached. However, because in this simulation, the mesh evolution towards the equilibrium is slow, the mesh refinement might be triggered before the equilibrium is reached. As a consequence, once the mesh becomes highly refined, its evolution towards the equilibrium becomes even slower. And, as you can see here, the simulation time to reach the equilibrium becomes unreasonably long. However, the solution to avoid this problem is simple. Let's stop this simulation. And let's reload the initial configuration we saved before. To avoid the problem of the mesh getting refined too much before the equilibrium is reached, we simply need to select a lower target refinement for the mesh. In this way, the mesh will keep its refinement not too high, and this will prevent the simulation from becoming too slow. In addition, we enable the option to keep the mesh boundaries sufficiently refined to avoid problems due to the solid surface concavity. If now we launch again the simulation, you will see that the mesh will maintain, for the whole simulation, a not too high refinement. And this will allow the simulation to evolve the mesh toward its equilibrium shape within a faster time. So we now wait until this not too refined mesh has reached its equilibrium shape. And this time, the simulation time to do so will be reasonable, thanks to the mesh being not too refined. Then, once the simulation will be completed, and this not too refined mesh has reached its equilibrium shape, we can launch a new equilibration to refine the mesh to a higher degree. Since, at that point, the obtained mesh will be close to its equilibrium shape. So, the simulation to refine it further will be faster. As you can see, the mesh has now reached its equilibrium shape within a reasonable time, and the simulation is completed. The simulation time was not too long, because we selected a not too high refinement for the mesh. We can now improve the refinement of this mesh by selecting a higher degree of refinement in the simulation settings, and then launching a new equilibration. And this time, even if we selected a very high degree of refinement for the mesh, the simulation time will be not too long, because the mesh's initial shape is already close to its equilibrium shape. So, to sum up the advice that I just illustrated you, when the initial shape of the fluid interface mesh is far from the equilibrium shape, and when the equilibrium shape is not trivial. For example, because the three-phase contact line is very long, as in this case. Then it is recommended to launch the equilibration, selecting a not too high degree of refinement for the mesh. Then, once the equilibrium shape has been computed for the not too refined mesh, you can launch a new equilibration to further refine the mesh, if desired. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.